Our third speaker this morning in this session is Sunil Mohan from Intel Corporation, who is a SOC design engineer. He's going to talk about hybrid architecture validation. He's a senior validation engineer at Intel in the E-core team with deep expertise in both emulation and post-silicon validation. He is currently the post-silicon debug lead for the E-core team. He has worked on multiple generations of the E-core product line, including those that are part of the recent 13th generation Intel core processors. Okay, thank you.
Thank you, Mike, for that introduction. Good afternoon, everyone. My name is Sunil Mohan. I am a senior validation engineer with Intel, and I'm part of the E-core validation team based here in Austin. Today, I'm going to talk to you about some of the validation strategies and challenges that we faced during our hybrid architecture that we introduced recently. Over the course of today's presentation, I'll give you a very brief introduction to what our hybrid architecture looks like. We'll talk about some of our pre-silicon challenges and solutions. We'll visit our post-silicon functional validation methodology. We'll briefly touch upon what our OS-based verification looked like, and then we'll wrap things up with a quick overview of what functional validation sign-off looks like. So, to get started, our hybrid performance architecture is designed to deliver high-efficient compute performance in a large dynamic range of power and performance. Traditionally called heterogeneous computing, our implementation of this has two core types, E cores or efficient cores, and P cores or performance cores implemented on the same SoC. Our performance cores are larger, high performance cores tuned for high IPC, supporting higher turbo or burst frequencies while supporting hyper-threading. Our efficient cores are smaller, they're physically smaller, with 4 E cores being able to take the space of 1 physical P core. We are designed to maximize CPU efficiency and are ideal for scalable multi-threaded applications while not supporting hyper-threading. So let's get into how pre-silicon verification worked for us. We took a 3-prong approach to our pre-silicon verification. We had dedicated CPU teams, and I'll talk about this in a little more detail in coming up slides. We had dedicated CPU teams, the E-core validation team and the P-core validation team, who worked in conjunction with an SoC team to get the entire product out of the door. Now, to be completely fair, there were many other IPs that were part of this process. In today's presentation, I'm going to be talking mostly about the CPU, but USB, graphics, PCIe, audio all played a very crucial role in getting this product out of the door. So, what did we do with these tricks and why did we split them out? Now, the 2 core types, even though they support the same instruction set architecture, have different microarchitectural implementations. And having different microarchitectural implementations ended up meaning that the validation teams were experts in their own microarchitecture. This makes us, each team, the best people to validate this thing. It allowed us to validate our IP in isolation, our idea being that we could run our existing workloads, our existing test generators, and make sure that a given core in isolation worked properly. And then obviously we collaborated with our SoC teams to make forward progress, helping them do integration debug, validation at an SoC level, and solving general issues. Our SoC team took on the more crucial task of integrating all of these IPs together, including the 2 new cores together, doing all of the hybrid workload runs. Hybrid workloads runs in this case is a combination of running our existing test generators, which didn't really care about the different core types. They just saw multiple cores. You run the workload, see what happens. We did have to enhance a couple of our test generators to actually make them hybrid aware, tell them that there are 2 different types of cores, and see how task switching works in these. They helped verify key performance indicators. Key performance indicators for us is both power and performance. It also includes making sure that Intel's thread director technology came into play. If you have not heard of what Intel's thread director technology is, in the Windows world, it's called Intel's thread director technology. Linux calls it HFI. It is what allows an operating system to be hybrid aware. It gives the operating system real-time feedback as to what's going on the SoC, both in terms of power, performance, and also thermal limits, allowing the operating system to make the best use of the available resources for the given workload. So making sure that thread director technology started to work in pre-silicon was also a challenge. And then helping to coordinate debug across the various IPs. We have multiple IPs on this board, making sure that all of these IPs got debugged, pulling in people across multiple domains as the case may be, was a challenge that was sorted out by our validation team. So periodic consistent check-ins between the course and SOC allowed us to make forward progress and go through most of our pre-silicon validation. Now, one of the things that we had to sort out as we went through pre-silicon validation was to get microcode sorted out. Now, microcode for us is the glue that stitches our instruction set architecture to our microarchitectural implementation. With two different microarchitectural implementations, this means that the two cores, the E cores and the P cores, have different microcode implementations. And so we had to make sure that the P core microcode and the E core microcode played well with each other. Why is this important? There are two specific contexts for which this is important. A, you've got two different cores that are now talking to shared resources on the SOC, for example, graphics. So it is important that the microcode implementations on both core types are talking to the same register offsets. Otherwise, things are not going to work as expected. In a task switching context, typical task switching gets implemented in some form of an X-save and X-restore instruction, where the operating system is saving register state on one core, saving it to memory, and then restoring it back using X-restore instruction. So it becomes vital that the two microcodes implement memory ordering the same way. If you don't implement memory ordering the same way, you're going to have one core save and save in one order. If it doesn't restore in the other order on another core type, you're going to get into trouble. So getting the microcode working between these two cores was also an important challenge. And to do that, we ended up building a combined microcode simulator model. We took our P core microcode, we took our E core microcode, put them together, and built a simulator that could run microcode together. This allowed us to start validation of this interaction of the microcode before a full-blown SOC emulation or simulation model was available. Our implementation allows us to execute both macro instructions, assembly instructions, alongside microcode. And this gave us a vehicle to be able to do faster turnaround of some experiments that did not need a full-blown emulation or simulation run. This also proved to be very effective and useful for another task that I'll come to in an upcoming slide. So getting through microcode emulation, getting through microcode validation, along with all of the other standard pre-silicon flows, we made forward progress. And before we knew it, it was time for silicon. For post-silicon validation, we ended up doing a similar approach. Our pre-silicon approach for three-prong worked out really well. We basically replicated that implementation back down into post-silicon. Again, we had dedicated post-silicon teams doing IP level validation to the extent possible. This is post-silicon, so isolation of the course is a little more complicated, but to the extent possible, the two CPU teams did their IP level validation, and the SOC team came in and ran their full-blown post-silicon validation. Similar things to what was done in pre-silicon, but with a lot more focus because the stakes are far higher. We have hybrid silicon at this point, it has to work. So running the hybrid workloads, it's all well and good to build a test suite that just moves things around, but does it actually work in silicon? Making sure all of those things worked was a key task that the SOC team did in the space. Verifying our key performance indicators was another important challenge. Key performance indicators for us are both power and performance. So making sure that our pre-silicon numbers started meeting post-silicon numbers. The realities of what actually showed up in the lab was what expected. And also making sure that our product landing zone targets were in sight. And if they were not in sight, going back and making sure that things in that space got sorted out. And another challenge that had to be faced out was coordinating debug with IP, with the appropriate IP teams. You're running complex workloads, operating system-based workloads. You could have failures that show up from either core type or from a completely different IP. Figuring out where the problem was and figuring out how to sort that problem out was a challenge that the SOC team helped to drive. Now, this is all well and good. And as we went through this process, there was a question that occasionally came up back and forth between us. And the question had to do with, what if our synthetic workloads are not stressful enough? Now, we have seen on previous generations and previous projects that external software can have corner case behaviors that our test generators just don't model. We have seen external software do things that are not completely up to spec. For example, using reserved bits and registers. If the two core types don't understand that these register bits are reserved, we might end up with unexpected behavior. And we wanted to see how random task switching might actually behave and work. It's all well and good to build a synthetic test suite that takes two tasks and switches them back and forth. But how does this work in real life? To try to answer some of these questions, we turned to open source software. We looked at open source schedulers to see how they actually implement task switching. We were able to, remember I said a couple of slides back, our microcode simulator model can actually run assembly instructions. So we made use of that here. We took the open source scheduler software, we compiled it down, and we ran it on our emulation, on our microcode validation model. This gives us the ability to actually see how the scheduler would work long before we actually got to full-blown models. And we ended up building a randomized task switcher. The randomized task switcher is an application that we built to figure out how this would actually work. In PostSilicon, you point at an application, and in a randomized fashion, or a directed fashion, depending on what we wanted to do, it would take an application and force the operating system to move things back and forth between between the E-cores and the P-cores, and figure out how this worked. So let's see what and so now let's see what our functional validation sign-off look like. Our functional validation sign-off, this is functional validation sign-off, so this is above and beyond what is traditionally called sign-off in things of DRC and timing and convergence and stuff. Functional validation sign-off for pre-silicon looks at pass rates for synthetic test content. We want to make sure that our synthetic test content has acceptable pass rates. What is acceptable pass rates is a highly subjective question, so figuring that out is important. We wanted to make sure that all failures are understood and accounted for and dispositioned properly. We collect a lot of coverage data in pre-silicon, so coverage analysis and coverage closure, as everybody knows, is an important part of our sign-off requirement, making sure that things work. And in pre-silicon, we do look at our power and performance data and make sure that they actually meet our expectations to what is architecturally projected. In post-silicon, our sign-off is similar. Again, we expect to have some acceptable pass rates for synthetic test content. Any failures that were seen in post-silicon have to be accounted for, understood, and dispositioned in a similar manner. We wanted to make sure that our power and performance data here in post-silicon also meets our expectations, both projection-wise and towards the product's eventual target landing zones. We insisted on having 100% pass rate for our OS switching tests. The simple scheduling application that we built and pushed things around, we wanted to make sure that was running absolutely clean. If anything failed, we wanted to understand why it failed and help sort that out. And then having thread director work as expected. So thread director's implementation in Windows is thread director. In Linux, they call this HFI. Making sure that that is working as expected, both in terms of ensuring that actual task switching was working and that we were actually providing the correct data to the operating system schedulers so that they can sort out where they want to land their workload. So with that, I will give you a couple of our references. I do want to call out Lakefield as a product. Our introduction of hybrid architecture actually came out on this product that we call codenamed Lakefield. It came out in early 2020. A lot of the stuff that I talked about in my previous slides was originally developed and path cleared on Lakefield and then enhanced and expanded for what eventually became Alderlake and Raptor Lake. And so with that, I'm happy to take any questions.
Any questions from the audience? But I guess the main question we have online is what's the you seem to split the vocation up into those three areas that you talked about at the beginning, the two different IP related to the SoC. What would you say is the main advantage and disadvantage of breaking it down into those?
Okay, so the question is, why did we split the verification down into the three prongs? Advantages and disadvantages. So advantage of that is it allows for differentiation and focused validation of the area of expertise. The two CPU cores have different microarchitectural implementations, and therefore you needed the IP teams who are experts in their area to actually make sure that their cores worked. It also allowed the teams to make sure that their cores in standalone worked properly before trying to work alongside the other core.
Okay.
It prevented roadblocks in case one core had issues that needed to be debugged, the other core wasn't stuck waiting for them to solve their problem. The SOC team, their expertise across several generations is bringing things together.
Okay.
And so they were the best positioned to be able to run our hybrid workloads.
Okay. Okay. Thank you very much. That's probably the main question online, sir. Okay, so that takes us nicely into the lunch. So thank you very much to Sunil. So we've got an hour now. We're all back in here at 1:30. So yeah, so there should be lunch out there now. It should be there to go and grab a lunch and find a place to eat it. Okay, thank you very much. See you this afternoon.